All right, welcome to this week's discussion hour. This week we're going to have a talk from some JSG alumni, which is super exciting. We've got Ted, Kiran, and Kris, and they're going to talk to us. They're all from Novi Labs, and they're going to talk to us about machine learning and geology, and their talk is called Novel Methods for Practical Machine Learning Applications, Principal Components Analysis, and Shapely Values in the Back and Three Forks Play of North Dakota. So I'll let them take it away, and then we can have a chat afterwards.
Thanks, Naoma. Good to meet everyone here today. I'm going to go ahead and share my screen. I've met some of you before, so good to see you or hear from you, et cetera, et cetera. Okay, can everyone see my screen?
Yes.
I'm looking for thumbs up.
I can see it.
There they are. Yeah. Okay. So Naoma already went over our talk there with the title, but we do intend for this to be a pretty informal discussion with you all. Kris, Kiran, and I are all recent or somewhat recent alumni of the JSG. And so we thought, happy to discuss anything like transitioning into, working in industry or in software, anything like that. So one thing's to be pretty informal, and want to also tell you a little bit about where we work, Novi Labs, here in Austin, a little bit about our backgrounds. And then we're going to transition over to the technical topic for today. And before hitting that, I want to hit you all with some basic kind of problems with machine learning and with geosciences in oil and gas. So we have to deal with a lot of kind of niche difficulties that generalize to other things within machine learning and the geosciences, and so hope to talk to you about that. Then we'll go through the research presentation, end with like kind of a short kind of demo of how our actual software works, and then of course, leave plenty of time, hopefully, for questions and discussion. I will say, if you want, feel free to just interrupt us at any time if you have any questions. We have, a focused group here today, so I don't really worry about that. Okay, so about Novi, we are an Austin-based startup focused on developing machine learning solutions specifically for unconventional oil and gas development. And I'll tell you more about what unconventional oil and gas development is in a minute. We were founded in 2014, which may seem a little old for a quote unquote startup, but we only received our Series A funding round, which is kind of in the venture capital parlance, that's kind of your first major chunk of funding that you receive. And so you almost maybe want to start your clock from when you receive your Series A than kind of your initial founding. And that was only in 2019. Our customers are mostly operating companies, and that ranges from very small shops of like maybe 20 people all the way up through super majors. We have 22 employees, and it's a mixture of software engineers, data scientists, project managers, petroleum engineers, and geoscientists. And of those 22, I think we counted 6 are UT alums, including 3 from the JSG. So Kris, Kiran, and I are all alums, and we also have someone from software engineering. We have a petroleum engineer, and then we have a guy with a business background, all from UT. So happy to continue our connection with UT, and it's been a great source of talent for us as a company. So a little bit on each of us here. Maybe we should go through this individually. Kris, you wanna say a little thing about yourself?
Yeah, sure. So my role at Novi is data scientist. I've been with Novi since March of 2019. And prior to that, I was a data scientist at a company called Slingshot Aerospace, also a startup in Austin, for about 9 months. I graduated from UT with my PhD in 2018, working with Peter Flemings on like methane and carbon dioxide hydrates. And in particular, I focused on developing some Python software.
Awesome. And I'm a technical advisor at Novi Labs. Before coming to Novi, I was a geologist at ConocoPhillips, and I was there for 5 years. And so I get to take that kind of 5 years worth of oil and gas industry experience and kind of apply it at Novi. So I kind of interface in between our data science team and the outside world. I'll write technical papers, I'll go in sales meetings, I'll consult on difficult projects, and then do a lot of work internally with like deciding, what product should we build, how are our models looking, that type of stuff. I had my BS from UT Austin in 2011, so only undergrad, and then I had my master's from the University of Arizona in 2014. And I feel like I goofed up here. Now, Bill Carlson, my old undergrad advisor, has signed on, and I put my master's thesis topic here rather than my undergrad thesis. But for my master's, I did structure and stratigraphy in the thrust belt of central Nepal. But undergrad, and actually, Bill, you're gonna love this. I was just unpacking my books. I just moved, and I discovered my undergraduate thesis. Epitaxial nucleation of coronal metagabros, or something like that. So anyways, found that it was cool to see that. So metamorphic petrology all the way back there. So, okay, Kiran, you want to introduce yourself?
I was just muted, as normally happens in these things. So I started my PhD at UT in 2010. Mark Hess's group, finished in 2016. And focused on natural carbon dioxide gas fields. So that was kind of where I got an interest in commingling public data and just seeing what else is out there in terms of unused data, which is a lot of what we do here at Novi. Between working at Novi, which I started at in summer of 2018, and finishing my PhD, I worked as a data engineer at Snapchat. So I was basically coalescing and trying to make sense of all of the data that comes off of millions of the world's smartphones. So been able to put together kind of those two spheres and combine them into my work here at Novi. And my first year and a half or so at Novi, I worked as a data scientist, more similar to Kris's role, more purely technical. And now I work as a customer-facing technical advisor. So that's also been interesting, working both the technical and business side of things since I've started Novi.
Awesome. Thanks, guys. Okay, so what's our technology stack? You'll see the data science side is more complicated than it is on the actual customer-facing side. But the data science, we actually have a lot of stuff which is open source. Mostly we use kind of Python as far as our data science goes for the main programming language. We have some heavily adapted versions of basic machine learning pipelines from scikit-learn, things like XGBoost. We use Docker for our software deployment, GitHub for our code control. AWS is essentially where everything is hosted for us, and we use a lot of their accessory services. And then when it comes to analysis, visualization, prototype development, et cetera, we use Jupyter Notebooks, Matplotlib, and Kris, I don't think I actually know what that little graph chart is down there.
It's Altair. It's a terrible logo. I don't know why the name's not there.
Okay, that's Altair. Everybody's learning something today. And then when things comes to review stuff with customers or deploy it to customers, a lot of them are using Spotfire to kind of analyze the data. So that's what's known as a business intelligence client or business intelligence tool. It's basically like Excel on steroids, for kind of slicing, analyzing data, joining different tables together. And all of that is hosted on Amazon Redshift, all of our data. Okay, so next I want to kind of walk you through some unconventional drilling basics, since you need a little familiarity with this if you're going to kind of understand our research presentation. The basic idea behind unconventional development is that you want to take rock which is low permeability, aka the hydrocarbons or the fluids can't flow through it very easily, but still has a lot of oil or gas stored in it. So it has good storage, it has good fluids, but it's impermeable. And so in order to get those hydrocarbons out to the surface, these companies use a combination of two basic techniques. One is horizontal drilling, where they'll drill down for 7,000 to 15,000 feet vertically, and then they will turn 90 degrees, once they reach the good stuff, where the hydrocarbons are, and they will then drill through that layer of rock for between 5,000 and 15,000 feet. To essentially increase their contact with the rock. So if you imagine you drill a vertical well through that, and you're only draining 600 feet around your vertical well, you're not draining very much with that. But if you drain 600 feet around a 2-mile long horizontal well, you can drain quite a lot. So essentially, it's increasing the surface area of your kind of drainage volume. The second component that goes along with that is hydraulic fracturing. This is commonly known as fracking. And that is essentially you pump a bunch of sand, water, plus some chemicals, things like surfactants and lubricants to help you overcome the friction over 4 miles of pipe. So then you pump that down into the wellbore, into perforation. So you actually kind of shoot little holes into the rock, and you pump that fluid through that. That increases the pore pressure of the rock, and causes it to fracture. So that's the basic idea. Is it's a combination of increasing surface area and then increased permeability, artificially enhanced permeability with those fractures. So if you're an operator and you want to go do one of these horizontal developments, you have several things that you kind of options to choose from. First off, where are you going to drill? Where do you want to lease up? And for your lease, where do you want to drill? Second question is, how closely do you want to put your wells together? Third, how much sand do you want to pump? How much water do you want to pump? There's some details about how you can kind of break that hydraulic fracturing treatment into stages. You don't want to try and pump in the whole thing at once. So you kind of break it up into different stages. And then, once you've done that, how you produce the well. So, like there are different, do you want to put a pump on it? What kind of a pump? Do you want to let it flow naturally? Like those types of choices. Okay, so now I want to switch gears to kind of discuss some problems that we run into, with machine learning and unconventionals, and that also kind of apply to geoscience more broadly. The first thing that we run into a lot is that within unconventionals, we have lots and lots of data. You're onshore, you have thousands of wells, maybe even hundreds. Like in the Permian, you have over 100,000 wells. You may have tens or hundreds of thousands of well logs. So those are those could be sonic, gamma ray, neutron, nuclear magnetic resonance, lots of advanced kind of logs. So lots of great data. You have hundreds of cores, to help you calibrate all that other stuff, actual examples of your rocks. But even with all that data, the actual physical processes for unconventional oil and gas production are still poorly understood. I mean, I've heard like reservoir engineering advisors argue over whether the molecules are actually how they're actually flowing to the surface. Is it some kind of is it diffusion? It may have, like, some of them are speculating there might be molecular diffusion along the surfaces of the grains. I mean, it's like what's happening at the fundamental level on the rocks is actually still poorly understood. So that runs us into some issues. I do want to note here, especially since we're talking to UTIG, that seismic is relatively rare. Some of these companies may go through full unconventional field development without ever collecting any seismic data. And that's because they may have a density of well log data that it's not necessary to collect that seismic. And it also is because to collect that seismic over like the field scale may be prohibitively expensive. Literally, it's easier when you're working offshore and you're dealing with a more kind of discrete conventional field rather than one of these unconventionals that spreads out over gigantic areas. So we run into lots of issues with collinear variables, so variables that are highly correlated. And this is especially the case with an unconventional development because they're relatively, tectonically straightforward basins for the most part. So things like depth, pressure, rock maturity, depositional phases, geomechanics, those may all be strongly correlated. And that causes issues with machine learning models because they're just looking for empirical relationships. And if you feed them a bunch of things that are collinear, these, number 4, number 5 on this list may not really add any additional information that's not present in number 1 or number 2. And then all of machine learning deals with the issue of lack of interpretability, that as opposed to, let's say, a linear regression where you can see the equations that were used, machine learning is often thought of as a black box where it's either kind of the inner workings are too complicated or it's just kind of so many interlocking components that it can be difficult to understand how the model is coming up with its predictions. Okay, so a little bit about what we do for Novi. We build machine learning models and we have a piece of software that kind of works around that. So the first step in that whole process is the model basically learns how different variables like geology, your hydraulic fracturing design, well spacing, how those impact the outcomes, which are oil, gas, and water production. So for us, that's of interest. Then once you've trained that model and has learned that kind of, what's generating those outcomes, you can then use that to get answers to questions like, what is the optimal well spacing? How much will the new well that I'm drilling at the end of this year produce? And how much proppant should I put in this well? And the idea is that we have a front end piece of software that I'll show you at the end that uses those models to help you answer those type of questions. And customers will be interested in those questions. The answers will kind of depend on, okay, how does that change my estimated ultimate recovery for a well? Like, how much is it going to produce over its life? What's the net present value? What's the rate of return, of these investments? And those are, NPV and rate of return are like two of the very most common economic metrics that we deal with within oil and gas. And I will say one more note is that 95% of the time we take over after the geoscience data has been already prepared. So the customer has done basis classification, multi-mineral model, seismic inversion, whatever they're working on, they've already done that and they hand it off to us. This talk today is a slight bit of an exception where we're kind of working directly from the logs that are provided by a state regulator. But 95% of the time, this kind of, we start once that's already done. Okay, so now we're going to switch gears, and Kris is going to, we're getting into the meat of the research presentation. So Kris will take over here.
Yeah, so I'm going to present a few slides, and then Kiran's going to.
Sorry, that was my bad. I accidentally muted you.
I don't know if you guys heard anything. So Kiran and I are going to tag team this. I'm going to do the front half, and he's going to do the second half. I'll basically explain how we built this thing, and he's going to tell you how we present it to other people and interpret it. So up front, I'll say that this is modified from a presentation that we gave at a professional conference this summer called UTIG, which is focused on unconventionals. So if anything is confusing, like, we're happy to stop and explain it in more detail. And the two things that are of most importance, I would say, with regards to what we're going to present, are that we make a novel use of principal component analysis. And then we'll talk about something that may be totally unfamiliar to many of you called Shapley values, which helps us explain what a machine learning model does. And then we'll finally describe how we coalesce all of this information together into something that we like to call GeoShap, which we think is new, that we've invented for the industry. And then just to reiterate once again, what we're trying to do with this model is we're trying to produce forecasts of oil production or gas production or water production for a 2-year period. So we're going to have a certain set of time points that are the output of a model where the features going in could be anything. Oh, you got to make it go forward, Ted.
I got you.
So the workflow summary is described here in this diagram at the top. This relates specifically to the rest of this talk, but more generally, it describes what we do for any customer and more or less what we think you should be doing for any machine learning model. So on the far left, you start with whatever raw information you can get your hands on. So for this presentation, that was logs, tops of formations in our basin of interest, and geochemistry data, but that could be some other interpreted information from a customer or anything else that seems to be valuable. We then turn that information into something that's one step more informative. So we may aggregate pieces of information. We may turn parts of that into a classifier or a mini model before we go on to the big machine learning model. So then finally, we have a set of variables, which we call features, which describe everything we could possibly know about our data set. But oftentimes that's quite large. And in fact, it has redundant information. So we do something like kernel PCA to trim down the amount of information. And then with that, we have our truncated, reduced form of our features that then go into the machine learning model. That machine learning model is trained to then predict something like oil over a 2-year time horizon. And then finally, we take that black box of a machine learning model and we pass through an algorithm that produces something called SHAP values that then tell us how a particular feature impacted the prediction that we made. And then finally, we bring that all together with the GeoShap. So what this workflow allows us to do is to be flexible for any sorts of inputs that we have or any outputs that we want to predict. It actually has really strong performance because we have dimensional reduction that allows us to not latch on to things that have spurious correlations with the targets. And then finally, it's interpretable so that at the very end, you get a good sense of how to rank features and how on an individual basis, why some features are more important than others. So for us in this specific thing that we want to discuss, what we did is we created a public model for the Bakken Basin using the North Dakota Industrial Commission website data. We took logs, and then from those logs that consisted of gamma ray, resistivity, sonic, neutron porosity, bulk density, spontaneous potential, in addition to mudlog gas measurements and gridded depths. We turned that into something that described each formation. So we got statistics on the individual formation. We had a zone classifier that allowed us to differentiate between a lower, middle, and an upper Bakken. And then all of that then was brought together to give us, on an individual well basis, 300 geology features, some of which sound like they could be redundant. So it could be like the P50 of this section for resistivity, or the P95, et cetera. And then from those 300 features, we reduced them to a set of features that was informative enough to capture what was originally a part of that feature data set, but then small enough such that we could have independence amongst the features, number one. And then number two, we did not overwhelm the model with lots of individual geology features that were secretly encoding something like location. Specifically, what we did is we applied kernel PCA, which is a cousin of PCA, where PCA allows you to take a set of data and then determine the dominant orientations of that data to then reduce the dimensions of it. The canonical example is that if you have a scattered line of data that sort of goes across the line, but primarily has a direction, you can then deduce that the data has a dominant direction, which is the slope of the line, and then possibly disregard the orthogonal dimension. This is problematic in cases where you don't have linear sorts of features that then can be decomposed in a linear way. So the example here is that if you start with data on the top left, which is this black, red, green concentric circles, if you apply PCA down below, linear PCA, it would do nothing to your data. You would get back exactly what you had because there was no dominant direction. But if you then invoke the principle of kernel PCA, it adds an additional dimension, which effectively means something like a radius. So that means that either if you use a Gaussian kernel or a polynomial kernel, you can then separate the lines or the points which were part of the smallest circle, the middle circle, and the largest circle. And then you can abstractly extrapolate this concept to as many dimensions as necessary. So from that, we're able to then produce 5 different PCA features, which do 2 things for us. Number one, we can visualize them across the entire basin and get a sense for how they relate to things we would expect to find in this basin. And then secondarily, we can see which of the original features were important in describing the new PCA features. So we have these maps which say color coded according to like a high level or a negative or a positive value. And the first GeoPCA _0 more or less corresponds to structure within the basin, even though we didn't tell it anything, it just figured that out on its own due to the kernel PCA that we applied. The second GeoPCA1 gives us something that we could possibly convince ourselves is like overpressure. And then the latter 3 tell us other micro things, including in GeoPCA _3, there is an anticline along this yellow line here that is well known, that's picked up by the kernel PCA. And then on the bottom, oh, actually, go back one, Ted. And on the bottom, you'll see that this table represents which were the important features in each of these individual PCA features, and it conveniently buckets all the things that you might think are similar. So in the first one, it's mainly formation tops and other things that would say something about depth. And the second, it's sonic logs. And then the third, fourth, and fifth, or the GeoPCA _2, 3, and 4, there's sort of a mixture of what could be chemistry information or some other pieces of information that could be useful if you wanted to go down that rabbit hole and figure it out. So then finally, what that allows us to do is make the machine learning model, which consists of a very finite number of features, but it provides a high degree of information for each individual feature. So what we have as inputs are the things that can be controlled, that we call completions. So that's the amount of sand you're injecting, the amount of water you're injecting, and how far away you're spacing each of your demolitions effectively. The spacing, which describes what your local neighborhood of wells around you look like. So if you're very close to some neighbor that's been in that field for 5 years, or whether you're going out into a new area and you have no neighbors. The timing, which is intertangled with the spacing. And then finally, a reduced set of the geology. And we need to also point out the things that we don't include are things which could give us good signal, but are not generalizable, such as the operator, the latitude and longitude, county or area, or some other post-drill things. And this is important in any machine learning model where two things you don't ever want to do, which are you don't want to ever include a feature that is really hiding and encoding a different feature that is more physical and intuitive. So latitude and longitude often tell us things about depth or geochemistry, et cetera, and it is itself just a proxy for something else. And secondarily, you don't want to include features that when you go to make new predictions in new areas, you don't have readily available to you. So if you can't produce it for a new set of a prediction that you want to make, then it's pretty much useless. Given all this, our algorithm of choice right now is random trees, and in particular, extremely randomized trees. So that's how we make our predictions. And we do the typical stuff of 20% testing, 80% training, which we can get into if anybody likes to talk about that. And then we make predictions that are 24 points. It's an entire vector, which each point is separated by a month, and it extends from the first month to effectively the end of the 2-year period.
All right, so I'm going to take over now. We're getting into Shapley values, and this is probably one of the most important kind of products we deliver to customers. And the general idea behind Shapley values, and this can be applied to any type of machine learning model for any application, is that it builds a model on top of a model with the goal of being able to quantify the impact of each of the features that train the model at a kind of per data point level. So this concept was adapted from game theory, came from a professor trying to ask on a group project, like how much does each person contribute or detract from the group being an average performing group. So our conceptual analog there is if I didn't know anything about the wells except for how much they were producing, the most naive prediction I could make was just to average all of the production profiles and then call that my prediction. And then as I learn more and more about each well and more about what makes a good versus a bad well, I can start to nuance that prediction away from the average. And so that's what the concept we're showing here on the left chart is. So the hot colors here represent a high value of the feature. So red on the proppant row represents a very large amount of sand pumped into the well. Same thing with fluid. And then the position on the x-axis represents how many barrels I'm going to move my prediction away from the average for that particular well. Each dot is one well. And this is showing our prediction of production at 720 days, roughly 2 years into the well's life. And we can do this at every time point. And we can do this across the 3 major production streams, oil, gas, and water. So when we show this to an operator, the first kind of like sanity check that will be checked is proppant and fluid both have a lot of red on the right. And what that means is that as you increase the size of the stimulation, more sand, more water goes out in the well, you expect to get more oil out. So that starts to check the boxes of this model is making some physical sense. And then we can get into much more nuanced questions about how does the size of the stimulation interplay with the timing and the spacing of the wells, and how does that how is that impacted by the type of geology that I'm in. So here we're showing the SHAP values of those PCA geo features. So this is basically showing me how does the model think each geology feature in isolation affects the production of a well. So unsurprisingly, here on the far left, as you go deeper into the basin, we expect more hydrocarbons to be produced. So for the basin architecture folks, basically the Bakken in North Dakota is one of the geologically simplest basins you can think of. So most of that sweet spot right at the bottom is about 10,000 feet. If you apply a typical geotherm, that puts us right into the oil window. So that's where you're going to find really good production of oil, less gas, and there hasn't been too much burial exhumation going on there as well. So basically all the organics in the Bakken formation got buried straight down the oil window and stayed there for most of its history. So that's where you're going to find some of the best stuff. And that is exactly what SHAP value chart right here saying blue is the best right there at the bottom, which is roughly 10,000 feet depth. And so without knowing anything about geology or anything about hydrocarbon maturation, burial depths, anything right there, the model's starting to pick up something that makes physical sense. It doesn't always happen, but it's nice that it happened here. And then one of the other interesting things is that anticline we were talking about here in GeoPCA3, fourth panel, so it identified that there is an anticline right here. And then, but we don't know just from this chart whether it's associating an anticline with positive or negative production. So what we would like to see is that the anticline gets associated with a positive or uplift in production, as there has been some migration of oil going up dip. And the SHAP value chart tells us that. So we have higher values, expected production running along this anticline as a direct result of this feature, which has identified the anticline. So these are some of the quick ways that we can talk to our operator customers about how these models work, how they can use them, and how they can ensure that they're not just sticking data into a box and getting an answer out. They're actually verifying that it makes physical sense with what they know about the basin. And so the sum of all these geo features, this was actually invented by one of our operator customers and then stolen by Ted and put into an architect presentation. But he started just summing the SHAP values only for the geology features together to try to come up with one number for rock quality index, or just a very simplified version of where's the good stuff. And so we sum together all of those geo features I was talking about. And so some of the components here are coming from the fact that you have some oil that's buried very nicely directly into that temperature window where you can have the best oil production. Some of it's due to some anticline effects. So there's going to be a lot of these differing geological effects which could contribute to having a strong oil production potential. We sum up those SHAP values together, we get the best productive area is some combination of where you have the lowest depth down to that roughly 10,000 feet bottom of the basin sweet spot, plus some anticline effects. And that's what the map here is showing. The worst oil production areas are out here on the fringes where you haven't had as much maturation, and the best areas are going as deep as you can and also trying to stay close to that anticline. And so now we can just kind of roll up all those geology features into one. So here's another really interesting thing we found here. This was one of Ted's brainchildren here. On the left, we plotted that SHAP value on the x-axis. So this is basically how good is the rock you're in. And each one of these points on the scatter plot is a company, an oil producing company. And on the y-axis, we're showing the actual oil they produced in terms of barrels per foot. So remember, these horizontal wells go laterally, and one of the ways you can normalize for wells is to say, for every foot of lateral length they put in, how many barrels did they get out? And so you would expect operators that had the opportunity to buy into better acreage would be producing more oil. Largely, that's what you see in the trend. But the companies that differ from that trend are really interesting, because we kind of tell operators that if you see a company that's underperforming their rock quality, maybe then that's a signal that maybe you can go buy in that acreage because they're doing something wrong. If you see a company that's overperforming it, maybe you want to try to copy whatever they're doing because they seem to be outperforming their acreage. And so, it is highly correlated production, but some of the differing companies off that trend is also a useful piece of information. Okay, so another really interesting thing we were able to do with this GeoShap value is cut the data in a way that we can learn about the controllable parameters that an engineer has, and that's basically what intensity do I give to the stimulation and how closely do I space the wells together. Given that I'm already in this acreage, like my company has bought a lease on this acreage, there's nothing I can do much about that, but once I'm there, what knobs can I turn knowing that this is the rock quality that I've been given, this is the hand I've been dealt. So one of the questions we wanted to ask was, proppant is actually pretty expensive. Like, you have to buy this sand. And so what kind of rate of return are you going to get depending on what rock you're in? So does proppant have a bigger impact in higher quality or lower quality rock? And what we found is that you find the trend is a little bit more extreme if you're looking at some of the higher quality rock versus the lower. And we found similar things in spacing. So we were basically able to tell our operators, you can use this to figure out both where to spend that extra money to try to go bigger, and where spending that extra money to go bigger is actually going to be a waste. It's not actually going to get you anymore. And so another interesting thing that we found, which is a bit unfortunate for a lot of operators given today's lower oil prices, is that we made this kind of risk map out of the GeoShap, green being the best quality rock, and then yellow going down to red. And most of the best stuff has already been drilled out of North Dakota. So this is something that, and some of the green stuff left over is like cities and national parks and like inaccessible for different reasons. And so, this is an important piece of information if you're an operator looking to expand your position in North Dakota, just to be aware that a lot of the good stuff's already gone. This is something you want to know if you're the state of North Dakota, if you're going to forecast your future revenue streams. Operators are not going to be flocking to North Dakota in the same way they were, 5-6 years ago. And this was all kind of based on taking those raw well logs and feeding them through this model. And we were basically able to create this risk map that otherwise would have taken a lot of human time and effort by a lot of geologists, just kind of utilizing these machine learning methods combined with some intuition and domain knowledge.
Thanks, Kiran. Okay.
Yeah, Ted's gonna do the demo.
All right. Okay, 2:40. So I'm gonna give you guys the 3-minute version of the demo. But I do want to just show you a little bit of what about our software product does. We do a lot of these type of research projects, both to kind of like improve our product, and it's good kind of publicity for us. But at our core, we do have a software product, and so I'm logging into our forecast engine software here. And the idea is that we build a model, we QA it, QC it, like the one we've just showed you, and then after that we kind of publish that to our cloud-based software, and now the user can go through and actually interact with it. And I'll just show you kind of what I've worked up for this analysis. So there's this company Whiting up in North Dakota who went bankrupt back in April. They were basically the first casualty of like the coronavirus demand destruction destroying oil prices. I'm sure you guys maybe saw in the news, the popular news, that oil went negative. And in the kind of yellow polygon you see there, I have their acreage. And Whiting was a little unique in that they had kind of chunks across the entirety of the Bakken play. So you see they have all this stuff out here in the west that's not very good. They have this stuff over here in the east that's quite good. And then they also have bits and pieces that are just kind of strung across everything. And when someone goes into bankruptcy, a lot of times it's like, okay, let's circle the wagons and see, you know, if there's any good pieces of acreage or good assets that we can buy off of them, because they're a distressed company at this point. And so we ran a bunch of different kind of pads, some like hypothetical developments. We just kind of dropped them around their acreage to see, okay, how does the production actually change around the basin? And so we ran some forecast sets on that. You know, I won't show you the rest of the workflow here, but you know, we combined those with some completions designs and with some, you know, costs and, you know, oil prices and that type of stuff. And you can come up with, okay, how does my production expectation change at every well location? So here we have, these are production curves for wells. So if you haven't seen one of these before, it's cumulative oil production on the y-axis here. And on the x-axis, we have IP days, or days on production. So the wells come on at day 0 and then out to day, you know, 720, or two years worth of life. This is their expected production. And it, you know, it starts off quick, and then it kind of, the rate decreases as it depletes the pressure, and there's less of a driving mechanism to get it up to the surface. And if we average those across these groups, you get something that reservoir engineers like to call a type curve. And so, you know, the long and the short of it is that this partial infill area over here in the green, and this east hidden bench area there in the blue, the production expectation at both of those locations looks pretty good. You know, if you're making 250 to 300,000 barrels of oil over the first 2 years, that's a pretty good well. Whereas in this Missouri Breaks or North Nesson, North Polar area, those things are making more like 200,000 barrels a day, which is, or not, sorry, you know, they're making 200,000 over the first 2 years, which it's not the worst thing in the world. You know, you can still make money if the price is right, but compared to how you do at those other locations, they're a lot poorer. So if you were, you know, a company that actually still had a little bit of money in your pocket, and you were looking to acquire some stuff that, you know, you might be able to you know, make some good investments in, you'd be looking at this stuff here in the blue or in the green. So very quick use case for how you could actually use one of these models. It's actually, a lot of our customers right now are using our models for this exact type of an acquisition use case, where there's a lot of distressed buyers out there, or distressed sellers out there, and it's a good time if you actually, you know, have some money to go make an acquisition or make a merger. So it's something that a lot of people are using our stuff with right now. So anyways, we have 15 minutes left now. We're happy to take any questions about what we presented, our software, you know, what it's like working at Novi, anything that you guys are interested in.
Yes, if anyone has any questions, feel free to unmute yourself and just call them out.
The chat is also good if your microphone isn't working.
I'll ask one, since I know that we have some people who expressed interest in watching this recorded. I feel like a popular question might be, if someone wasn't looking to go into academia and maybe work for a company like Novi, you know, what are some things that you either wish you had done before leaving the Jackson School, or that you did do that really helped you?
Kris or Kiran, you guys want to handle that?
Yeah, I guess I was like about a year before I finished my PhD, I started like teaching myself a lot of these Python and software development type tools with the express intention of getting a job in the software industry. So like a lot of the software tools that we showed earlier are not just used by us at Novi. That's like, those are all pretty standard across the software industry. And then I guess the other thing would be companies like ours, or like where Kris worked at Slingshot Aerospace before this, like they're going to be on that kind of border between geoscience or geospatial science and data science. And that's where those companies are going to be looking to not just get someone with a software experience, because we're not software engineer statisticians, like, and that's where we can actually bring together those two types of skill sets in a very unique way.
Yeah, I think it's a bit of an uphill battle for geoscientists to break into data science, and it helps if you have that career goal in mind to start as early as possible. like getting familiar with APIs and what it means to write software and the nitty-gritty details of doing machine learning. Because at the end of the day, we build software that helps produce oil forecasts and calculate the amount of return on an investment, but the generic tools can be applied to anything. So like if you wanted to forecast the amount of solar potential at a solar wind or solar farm, many of the tools would be identical. Or if you wanted to start looking at enhanced geothermal systems, at the heart of the data science toolkit, it's going to be the exact same. So if you can build that up, then you're going to be really competitive in the marketplace.
Yeah, and I'd also say like, you know, late stage PhD students probably don't feel like they have all the time in the world, but you know, there's a lot of things you can do within your thesis and within your like publishing goals that would get you started down this track. So any data processes you're doing, like just try not to use Excel, try to move it over to Python, try to automate as many of these tasks that you find yourself doing over and over in terms of data ingestion. Like those are things that are they're actually not only going to not eat into the time that you are applying to finishing your thesis, they might actually speed you up.
Totally.
And put it online. Use GitHub.
GitHub.
Show it off.
Cool. We've got a question in the chat here. It says, do you prefer work from home or would you prefer to be in the office in this type of job? Is work from home the new norm for tech?
I mean, I think we were actually set up pretty well to work from home originally. I mean, the software companies broadly are kind of set up for that type of work. We had basically our entire communications and software collaboration stack was already like up and running. So for us, it was just kind of like, you know, we had remote workers. It wasn't like a huge deal to start working from home. I miss going into the office, but I'm like a social guy. And you know, it's like you lose out on some of the informal conversations. Some of those might be, you know, making fun of our, you know, chief data scientist obsession with Tottenham Hotspur football club. But you also, it's like miss out on just like somebody's like, hey, what's going on with, you know, pressure or, you know, something like that. And then, you know, you spin off and do a 30-minute discussion. So I don't know if it's going to be the new normal. I think we'll see it. Definitely, I think remote is going to be more accepted. But in terms of like, you know, I think it remains to be seen how many people are actually going to be kind of required to go back into the office within the tech industry. Yeah,
I think it just really depends on the type of role. Like pure mainline software engineering, I think is doing great at home across the industry, especially talking to folks back in Silicon Valley. Like I don't think those guys ever skipped a beat. But think about like me and Ted and Kris do is also, it's similar to academia in that like, do you think you would be coming up with as many good ideas and as productive without those in-person? Like think about your experience over the last year. Like how many conversations have you missed out on academia because you just haven't been sitting there in the same space together? So I think our companies, I think we're going to settle on some kind of hybrid thing. And I think those top-down roles where the pure software engineers just get a blueprint and they have to write the code, I think those are going to be just fine from home, probably be home forever. But part of tech is also creativity, and that is always going to benefit from in-person interactions. And then the thing that I miss the most is actually traveling to meet these companies. So, you know, we learn a lot getting peppered from people that are skeptical about us or want to learn more. And, you know, we would meet like all different types of disciplines within a company. When we don't do as much of that anymore. Now we're only kind of talking to one or two people from a company. So I'm ready to go back to the office for those reasons. So yeah, that's my answer. I don't know, Kris, what do you think?
I really do like working from home, but part of that is my personality, number one. Number two, my team's dedication to using remote tools. So we use a software called Notion to capture any and every possible team meeting note so that there's a compendium of things that anyone has ever talked about, and it's all completely open and public. We check in with each other all the time, at least once a day, using Slack, which I think at least half of you are probably familiar with. But also the nature of the work requires many hours at a time for me to be very focused and uninterrupted. And if my job were a little bit different, where I had to do more of that creative teamwork using a whiteboard, it would be very problematic to do that from home.
I have a question. You guys are obviously Jackson School alums, but most of your, or maybe not most, but a lot of your company is not geoscientists. Do you feel like you actually use your geoscience expertise very often, or do you think that it's like you're mostly using your machine learning like type capabilities, and it just so happens that you guys majored in geoscience things?
Yeah, I guess I was the first person with any kind of geo degree hired at Novi, and that was several years into the company's life. So I wouldn't say that on a daily basis I'm like really doing geology, but I think a company like ours would really struggle without at least one or two people that can have those conversations coming from the oil industry. And like the example of the presentation you saw today, like it not only like assuages a lot of fears that a lot of folks have in the industry and have had about like the black box problem of like, why should I just trust like random numbers that come out of a machine that don't have any physical basis? And so I think that that's kind of the most important thing, is to have people that understand the physical basis so that we can, both sell more effectively, but also train our operator customers to use it more effectively. Because if they're getting answers that don't make any sense and we haven't helped them along that process to avoid that, then they're not going to come back and use it.
Yeah, and a lot of times we'll also run into, it's like, I tell Kiran this, I think, before, where it's like, honestly, I spend a lot of my time just like trying to comfort geologists. Like that's like, and like hold the hand of like geologist advisors and stuff like that. Cause like a very common thing that we'll run into, like we were discussing with the collinearity of variables, it like all the time we will see that something like porosity, if you look at the Shapley values, it shows a negative trend with respect to oil production. They're like, your model says if I increase porosity, I get decreased production. Like what's going on? And, it might be that there's some other variable that maybe even had porosity in its equation that was, ranked very highly, and porosity added. The only additional information that porosity carried was how much clay is in the rock. And so, it's like, okay, we need to take porosity out and put clay volume in, that type of stuff. So, it's honestly like just trying to work with them, hold their hands, like talk them through it. I mean, ultimately we want to get to a really good model. And we want, like Kris spent a lot of time talking about trying to get features that are encoding what really matters, right? And so like getting to that, we have to use a lot of geology. But, for us, honestly, the most important thing is just like understanding the industry. Like the actual oil and gas domain is less, the actual geology subject matter is less important than like the domain knowledge.
Yeah, and then I think also it kind of takes a retraining in a way. Like you're still thinking about earth science, but you're not thinking about it at those like microscopic mineralogy type levels as much. So, like we'll get a question like, did you calibrate the gamma ray log? Did you, all of these kind of very intricate lab type things. And like, we have to figure out the nicest way to say like, dude, it doesn't matter. Like on these miles and miles time, like spatial scales, like you need to think about more of like that basin architecture level. And like that example of like, as you go deeper, permeability is going to go down and porosity is going to go down. And like everybody knows that, like you've all seen a burial curve. But then when I produce a machine learning model that says permeability doesn't matter because all that information was already contained in the porosity, because the only reason you came up with permeability is because you were basing on porosity. So that's where it's not just being a geologist, it's being a kind of like a statistically literate geologist. So it's not that we're not doing geology, but it actually takes another level of understanding of those earth science processes to maybe wrap your head around something which might be a little bit counterintuitive if you didn't have those kind of like statistical literacy.
Yeah, and I would say for me, 98% of what I do does not require a geology PhD, but the 2% where I actually utilize it turns our product into something that's like open source and generic into something that's really powerful. So if you found yourself at a company and you really liked it and you had just that tiny bit of domain knowledge that set you apart, that would be really valuable for your career and the company.
Great point, Kris. Okay, Bill's been raising his hand. Bill, you have a question?
Well, I do, as a matter of fact. Broadly, I'm kind of wondering how widespread is this approach in the industry? I mean, is Novi sort of just spearheading this thing on its own, or are you competing with a large number of other options? Just trying to get some picture for what the overall scene is.
That's an excellent question. I mean, I think most companies, at least above a certain size, will now have at least some form of like machine learning effort at somewhere within the company. You know, the kind of these companies have evolved through the life cycle of starting with just like basic data analytics or descriptive statistics, like how does proppant like cross plot with oil production, you know, and then now they have kind of moved down the cycle to more advanced things, algorithms, the machine learning, that type of stuff. I will say that even though a lot of these companies like have an effort around advanced analytics and machine learning, there really aren't that many of them who are using it to like populate their production expectation for the fourth quarter, or to, you know, decide what to do with a given design decision. We do, like in terms of tip of the spear stuff, we do see some customers who have actually are actually making it to that location, but it's pretty few and far between in the industry right now.
And the level of governmental interest, I mean, you mentioned various things about how this could be useful for public policy and so forth. Are you seeing any of that?
Pretty little. I don't, Kiran, Kiran's shaking his head. I mean, you'll like in North Dakota, you'll have like, you know, there's various, you know, regulatory groups and state groups and stuff like that that are intertwined with academia. So, you know, they might be still doing big physical modeling studies and like that type of stuff, but I think it's pretty rare for them to have this type of an application focus in terms of a machine learning application that's kind of forecasting production for the benefit of regulatory stakeholders. So
yeah, I think the closest thing you'll find to government is like a place like the Bureau or UTIG. Like,
yeah,
Penn State has a similar thing. So it's more academia than government.
Yeah, y'all might know better than us about like how stuff is penetrating at the Bureau, but
yeah. And then I guess the other thing I'd say is that from my experience working in the kind of the pure software industry, is that this is like the headline grabbing stuff like machine learning models and all that. But like in terms of my career when I was like back at Snapchat, the thing that like raised the most attention and like honestly the thing that added the most productivity is like just being able to automate data collection and cleaning, and like just being able to like within 5 minutes of someone like asks a very basic question about the product or the uses or you know, it was like from there it was like how many smartphone users do we have in Brazil, and like without people that think about these like very foundational data things, like that's something any company should be able to answer that question in 5 minutes, but you'd be amazed at how many can't. So I think we saw something with where our employees used to work for Statoil, Equinor, and they actually published kind of like a mea culpa on like some of their failures of the last 5 years. And one of them was like across 3 databases, like they didn't have agreement on like who the interest holders were in their leases. So it's like these companies have the most to gain from these like very foundational data cleaning operations before they could even get into like machine learning.
Yeah,
fascinating stuff. Thanks for a great presentation, guys.
You're welcome. Thanks, Bill. Yeah, it's not uncommon for us to go to talk to gigantic oil companies who have assets across the US or across the world, and they don't even have their own data organized. So they have to go to a third-party provider to get the public versions of their own data for like a global analysis. I'm not kidding about that. And yeah, that is mind-boggling.
Yeah,
okay.
They'll submit their data to the state. A public or third-party company will scrape that data from the state, repackage it, and resell it back to them.
Yeah.
All right. Well, thanks so much for the talk. I really enjoyed it, and I'm sure others did well as well.
Yeah, thanks, Naoma, for the invitation. Thanks to everyone for joining in. Feel free to reach out to any of us, via LinkedIn is probably the easiest way to find all of us. But Naoma also has our emails if you want to go that route. That's also a good way. I'm just volunteered you, Naoma.
No, that's fine. I'll CC you on the email that I send out with the recording, so then everyone will have it.
Okay, that's the easiest. Perfect.
Cool. All right, take care. Bye-bye.